Okay, so in this video we're going to have a look at all of trigonometric identities and equations in the AS Pure Mathematics module. And before we get started, just like the rest of these videos, I'm just going to quickly show you how these videos work. So let's have a look at that now. So when you are on one of these videos, if you click into the description, you can see the video there where I cover all of the AS Pure curriculum. And if you scroll down, you can also see all of the chapters. Now these will slowly be filling up until it is filled the entire AS Pure curriculum, so hopefully by the time that you are watching this video, all of them will be actually in the description and you can click and watch each chapter. If you click onto the video and click the link in the bottom left there, you can actually see all of the chapters that are within this video as well. So you can skip through and have a look at the pieces of that chapter that you are needing to have a look at for your revision. So that's how this video works. Hopefully that's useful and helpful. If you enjoy this video, please don't forget to like the video. Don't forget to share it with some of your friends. But with that being said, let's get started. Okay, so when it comes to trigonometric identities and equations, it is essential that you know the trigonometric graphs. So as you can see on the screen, I have 3 of the trigonometric graphs, and it's very important that you are able to do a sketch of these. These are quite accurate, the ones that I've done on the screen, but you need to be able to draw a sketch of them. So you need to know that for y equals sine x, it goes in the origin, and then we have these waves that go up and over every 90, or up and under every 90. So it goes over the 90, down through the 180, under the 270 and then back through the 360. And this graph here goes on infinitely to the left and right of the y-axis, but we need to know how to draw a sketch of that, and you're going to see why in some later questions. For the one below, for the cos graph, this has just been translated, or it's the sine graph which has been translated 90 degrees to the left. So you can see instead it starts at 1 on the y-axis, but then it follows a very similar pattern. It goes down through 90, under 180, up through 270 and up and over 360. And again, this goes on infinitely to the left and right of the y-axis, but it follows this pattern. The tan graph is very different. It does have these waves, and as you can see there are asymptotes at minus 90 and 90, and then each asymptote follows on every 180 degrees, and again that is to the right and to the left of these curves. So you do need to know these graphs, you need to be able to draw basic sketches of them, and this is going to be very helpful when we are solving our trigonometric equations, as I do use a graphical method. Again, there are other ways of solving trigonometric equations, but I do use this graphical method as I do like them, and I do think that it's important that you know these anyway, so it's always good to be able to use them for further elements. So do make sure that you can draw a basic sketch of all of these graphs and you know them very well. Okay, so within this is also some exact trig values. Now you should know a lot of these exact trig values from GCSE level, but these are just the basic trig values, or the exact trig values. Now some of these can be written slightly differently. For example, 1 over root 3 down here for tan 30, you could actually rationalise that multiplying top and bottom by root 3, and instead you could write it as root 3 over 3. That's absolutely fine, and of course you will have a calculator for all these questions, but there are some exact trig values that you should know, and also you should be able to then relate these to the trigonometric graphs, as we will see on some later questions when we are looking at solving them. So for now, all you need to do is you need to make sure you know these exact trig values, and you also need to know the method for finding them. Again, I'll link the video in the description for how to find these, so if you're not sure on how to find them or how to learn these, then obviously you can go and you can check the full video in the description. Okay, so the 2 main trigonometric identities that we need to know are these 2. So we'll start with the one on the left. We've got sine squared theta plus cos squared theta is always equal or identical to 1. Now this one is super important, as is the other one, but this one is very important. Now this can also be rearranged. We could minus cos squared theta to the other side, which would tell us that sine squared theta is also equal or identical to 1 minus cos squared theta. So that is another one of our identities. Of course, we could have also rearranged it by minusing sine squared theta to the other side, which would have left us with cos squared theta, which is identical to 1 minus sine squared theta. So you need to know that identity, and you need to also know these two rearrangements, as we'll be using these a lot throughout our trigonometric identities. For the one on the right, when we're looking at tan theta is equal to sine theta over cos theta, we can also do rearrangements of that. So if we multiply cos theta to the other side, we could also say that tan theta multiplied by cos theta, so tan theta cos theta, is equal to sine theta. And again, we could rearrange that by dividing both sides by tan theta, and we could say that cos theta is equal to sine theta over tan theta. So there are rearrangements of this as well that you need to know, but as long as you know the two at the top that I've highlighted, you should be perfectly comfortable rearranging them, and of course that leaves us with quite a few identities here. So really you only have to learn the main two, and then obviously how to rearrange them. But these are very important. I'd make sure that you had these written down on some exam revision flashcards so that you always had these to hand. As we're going to be using these for any trigonometric identity, we'll be using one or the other, and particularly with our trigonometric equations, so do make sure you know these very well. Okay, so looking at a trigonometric identity. Now as you can see here, it says prove that 2 sine theta minus cos theta squared plus sine theta plus 2 cos theta squared is identical to 5, or always equal to 5. Now this is just one example of lots of different types of questions. So of course you do need to practice quite a lot of these, but this is a really good one for us to have a look at. So what we need to show in this is that for all of this on this left hand side is going to be equal to 5, or is going to always equal 5. And we can go about that by using some of our trig identities. Now we don't have a tan theta in this one, but that's not necessarily to say that it won't appear, but obviously we do have our other trig identity that has sine and cos in. So if we're looking at this one, we want to think about how we could change this so that it just becomes one or the other. But maybe we'll have a look at expanding it first and seeing what we get. So if we expand the first one here, that's going to be a double bracket, and that would be 2 sine theta minus cos theta, and we'll go about expanding that. So we would write that twice. So 2 sine theta minus cos theta, and you can already see that we're going to get some squareds involved. So if we expand that, 2 sine theta times 2 sine theta would become 4 sine squared theta, and then 2 sine theta times the minus cos theta, and we're going to do that twice, so that would be minus 4, and you could write either sine or cos first here, but 4 sine theta cos theta. Again, that piece that I've done just there, I have skipped a step in my expansion. I did 2 sine theta times the minus cos theta, and the minus cos theta times the 2 sine theta, so just doubled that up in one step. We now have to do the negative cos theta times the negative cos theta, which gives us plus cos squared theta. Now we can move on to our second bracket. Now we've fully expanded that one, and our second bracket is this one here. So if we expand that as well, that is again 2 of those brackets. So sine theta plus 2 cos theta, and we're going to multiply that by another sine theta plus 2 cos theta. Okay, so if we expand this one, sine theta times sine theta gives us sine squared theta. Then we've got sine theta times the 2 cos theta, and we've got that twice. So again, that's going to be plus 4 sine theta cos theta. There we go. And then we have the 2 cos theta times the 2 cos theta, which gives us plus 4 cos squared theta. So we've got our two pieces, and we need to add them together. So we had a plus sign between these two. So if we add those two pieces together, and let's see what we get. So we've got the 4 sine squared theta and a 1 sine squared theta here, so that would be equal to 5 sine squared theta. We've then got these middle pieces, so we've got the negative 4 sine theta cos theta and the positive 4 sine theta cos theta, so they would just cancel out. And then we have the plus cos squared theta and the plus 4 cos squared theta, so that would be equal to 5 cos squared theta. Now we need to figure out how we're going to make this always equal to 5. So we have two options. We could change the sine squared theta into a cos, or we could change the cos squared theta into a sine. So let's just think about our identity, and we'll put one of our rearrangements. So let's change one of them. We'll say that sine squared theta, or we could go, in fact, let's just go with cos squared theta. We'll say that cos squared theta is equal to, always equal to 1 minus sine squared theta. And that's going to allow us to change this cos squared theta here into 1 minus sine squared theta. So if we go about doing that, we would still have the 5 sine squared theta at the start, but we would now have 5 lots of 1 minus sine squared theta. So just replacing the cos squared theta with 1 minus sine squared theta has now eliminated cos from our identity that we're looking at here. So again, we could have done it the other way around. We could have got rid of sine and replaced that with cos using our other rearrangement, but it's absolutely fine for this one either way, as long as we just have sine. So now we could expand that bracket. So we would have 5 sine squared theta, and that would be plus 5 minus 5 sine squared theta. There we go. So where are we going to go from here? Now, if we bring that up to the top, let's just have a look at what we've got there. We have got and let's just highlight it, 5 sine squared theta and a minus 5 sine squared theta, which means they're going to cancel out, which just leaves us with the plus 5. So we just have the answer 5. So because we've got the answer 5 there, we have obviously proved that all of that just simplified down to 5. So therefore we have proved our identity that the 2 sine theta minus cos theta squared plus the sine theta plus 2 cos theta squared is identical to 5, and we've proved all of that. So there we go, that's all we had to do. Obviously we only had to use one of our identities. We used this one just here, and again you could have done that a slightly different way by rearranging it, but again you'd have just got to the answer 5 because you would have had a 5 cos squared theta and a minus 5 cos squared theta, and it would have all just cancelled out and you'd have been left with 5. Okay, so moving on to our first trigonometric equation, this is going to be quite a tricky one. Quite a long one and quite tricky to fit all on the screen, but I think we'll just manage to fit it in. So the first part here says, show that 4 sine squared x minus 3 cos squared x is equal to 2 can be written as 7 sine squared x is equal to 5. So the first thing to notice here is that in our second part, we only have sine. So in our first piece here, we're going to want to try and eliminate this cos. So if we eliminate that, we're going to want to think about which identity would help us to eliminate that, and that is that cos squared theta is equal or identical to 1 minus sine squared theta. So if we replace that cos squared theta with 1 minus sine squared theta, it's obviously going to start getting us towards our final answer. So if we go about doing that, we have 4 sine squared theta, or sine squared x, sorry, because we've got an x in this as we're looking at an equation. That is going to be now minus 3 lots of 1 minus sine squared x. There we go, and that is equal to 2. Now if we expand that bracket, we've got 4 sine squared x minus 3, that's negative 3 times negative sine squared x, so plus 3 sine squared x is equal to 2. There we go. Now we can add together our sine squared x. We've got 4 sine squared x plus 3 sine squared x. That adds together to make 7 sine squared x. So you can already see we've got something which is matching that 7 sine squared x. We also have that minus 3 is equal to 2. And now we could minus 2 from both sides, or we could add 3 to the other side. Now looking at the equation up here, what it wants us to be written as, it says it's equal to 5. So we want to add 3 to the other side, which would give us 7 sine squared x is equal to 5. And there we are, we have showed that it equals that. So that would be our final answer, and we have shown that correctly using our trigonometric identity. Part B here says, hence solve for values between 0 and 360, including 0 and 360, that this equation here is equal to 2. So we're going to solve this equation, and we're going to give our answer to 1 decimal place, or our answers to 1 decimal place. So we'll have a look at this and think about how we'll go about answering this. Now, of course, this equation here we have just shown can be written as this equation here. Now that we would not be asked to do that unless it was going to be useful. Now the reason it's useful is the second equation that we have shown only has sine in. So we're going to be able to use our sine graph to find our solutions, and how we'll go about doing that. So at the moment we have 7 sine squared x is equal to 5, and we're going to go about solving it. And you'll notice this with a lot of these questions, that part that it's asking you to show it as how it can be written is going to be used in the second part of the question. So to go about solving this, we want to get what sine x is equal to. So if we divide both sides by 7, we'll know what sine squared x is equal to. So sine squared x is equal to 5 over 7. Now to get what sine x is equal to, we just need to square root both sides. So we're going to have that sine x is equal to, and don't forget when you square root you have plus and minus, so plus and minus the square root of 5 over 7. So there we go, that's what sine x is equal to, and now we can actually use our calculator to do shift sign and find the values there. And if we put that into our calculator, let's do the positive one to start with. So sine minus 1 of, and let me just type it in, the square root of 5 over 7. Let's have a look, let's just write this down. So sine minus 1 of 5 over 7 is equal to, and we get 57.688. So it wanted it all to 1 decimal place, so 57.7 degrees. If we do the same for our next one, so sine minus 1 of negative 5 over 7, and again just go into your calculator, sorry, the square root of, well, I've just realised I forgot to put the square root symbol there. Put that in, I had to type that in on the calculator. We'll go back, we'll put the negative 5 over 7, close our bracket, and for this one we get the same answer but the negative version, so negative 57.7 degrees. So we have actually solved our equation here. We've got two answers. We've got 57.7, and refer back to our ranges here. So it's between 0 and 360. But this negative 57.7 falls outside of that. So that's not going to be one of our solutions. However, it is going to be able to help us to find all of our solutions on our sine graph. So we're going to use these answers to see if we've got any other solutions. And this is where it comes into play that it helps to be able to draw the sine graph. And again, this is where you can use different solutions. You can use your quadrant method if you would prefer to. That's absolutely fine. But as I've said before, I think it's really important you know these graphs, so I always like to discuss them. So if we look at the sine graph and we draw a basic sketch of what it looks like, if we actually draw that, sine starts in the origin. Obviously it goes up to 1 and down to minus 1, and it goes along from 90, 180, 270, 360, and we'll go back a little bit as well as we have that negative value. And if I was to draw that in, and again it's just a little sketch just so we can visualize it, it would look something like that. So if we label on our points negative and the positive side, 90, 180, 270 and 360, and then we'll have negative 90 and also negative 180, and let's just imagine where these points are. So the points that we have, we've got 57.7, which would lie between 0 and 90, so that would be just there, and we've got the negative 57.7, which is between 0 and negative 90 just here. So in order to find all of our solutions, all we have to do is trace along between 0 and 360 and see where these points hit any other point on the curve. So we obviously have our 57.7 just here, and if we go to the right, we obviously hit the curve at another point just here. So in order to find that one, we can just think about on the graph. Now 57.7 is 57.7 away from 0, so to find that one on the right, we would just do 180 and take away 57.7. And if we work that out and turn it into a decimal, that comes out as 122.3. And there's one of our other solutions, and that's between 0 and 360. If we go down to the bottom one at the negative 57.7, and we go across from that, we hit the curve here, and if we keep on going, we hit the curve again here, and that is between 0 and 360. So we have two more solutions just there. So to find that one, if we add 57.7 to the 180, then that is going to find our next solution. So if we do 180, add 57.7, and make sure you type that in correctly, and there we go. That comes out as this one here, 237.7, and again we can do that for the reverse. For the one next to it, we can do 360, take away 57.7, and that gives us our final answer there of 302.3. Now, of course, there is another point on the graph, as I've obviously gone into the negatives. There is another point just here, but obviously that falls outside of our 0 to 360 range, so that's not going to be a solution that we can use. So the negative 57.7 we can't use, but we have got the 57.7, the 122.3 just here on that top part of the curve, and then we had also the 237.7 and the 302.3. So we have four answers for this particular question, so we would give them, we would say that x is going to equal 57.7, and paired with that, we've got x is equal to 122.3 on the top part, and then down the bottom we had x was equal to 237.7, and matched with that on the right there, on the right of that was 302.3. These are all degrees, so we would put degrees with all of them, and there we go, they would be our four answers for this question, all given to one decimal place. So as you can see, very important to know these trigonometric graphs, and obviously knowing how to do your inverse of sine, and just getting that to the point where it was sine x was equal to a number, so that we could actually find that amount in degrees and relate it to the trigonometric graph. So that's one type of question, and obviously you can have harder ones than this, and we're going to have a look at some harder ones as well. Okay, so looking at one of our harder trigonometric equations, you can see that it obviously doesn't look very nice. It says show that 10 sine squared theta minus 7 cos squared theta plus 2 over 3 plus 2 cos theta is always identical to or equal to 4 minus 4 cos theta. Then it asks us hence solve, and we've got a very similar question to what we've looked at before. But we're going to start with this first part and show that all of this comes out as 4 minus cos theta. Now straight away you can see that in our answer part there that we're looking to show that it's identical to, it has a cos in. So for all of the pieces that have a sine in or a sine squared theta in, we're going to want to turn that into a cos. So straight away we'll write down our identity for that, and that is that sine squared theta is identical to 1 minus cos squared theta. And we'll plug that in and see where we get to. So if we start by replacing the sine squared theta, we have 10 lots of 1 minus cos squared theta minus 7 cos theta plus 2, and that's all over 3 plus 2 cos theta, but we'll just go about simplifying the numerator to start with. So the next step for the numerator would be to expand that bracket, so we would have 10 minus 10 cos squared theta, and that is then minus 7 cos theta plus 2. So that's our next step, and now we're just going to think about whether we can simplify this. Now the only thing we can really do to simplify this is obviously to add the 10 and the 2 together. So we'll add those two together as they are our only like pieces on the top, and that would leave us with 12 minus 10 cos squared theta minus 7 cos theta. Okay, there we go. So at this point we need to think about whether this factorises. This is just like a trigonometric quadratic. If we think back to obviously looking at quadratics, we could rewrite this in terms of x. So rather than writing cos, I'm just going to replace that with the letter x and rewrite this as a quadratic. So if I was to rewrite that, it would look like this. It would look like 12 minus 10, and that's cos squared, so I would have 10x squared minus 7x. And I probably want to rearrange that so it looks like a normal negative quadratic, which is 12 minus, and then put the 7x, and then minus 10x squared. So this is going to really help if you are struggling to factorise trigonometrics when we have the quadratics and we're trying to actually factorise them. You can just write that the cos or sine or whatever we're using in terms of x and then look at it from there. So if we go about factorising that, we want to think about those numbers that multiply to make 12, but of course we can actually change this quadratic and swap back our brackets at the end. So just to make it a little bit easier, I'm going to write it as positive 10x squared plus 7x minus 12, as this is really nice and quick to factorise. Our factors here would be 1 and 12, 3 and 4, or 2 and 6. And you can obviously see that that is going to be one of those numbers, but we need to think about our brackets. Now it's unlikely that it's going to be 10 and 1, so we'll go with 2x and 5x and see if it factorises from there. Of course, if you don't want to factorise, you could type these into your calculator to get your solutions, but nice and easy for us to factorise. We have 2 times 4, so it's going to be that one there. 3 and 4, again take your time with this, but 2 times 4 would equal 8, and 3 times 3 times 5 on the other one would be 15, and 15 and 8 we can make 7 with. We're trying to make positive 7, so we would want positive here and negative here, as that is going to make negative 8 plus 15, which makes plus 7. So we've managed to factorise it. All you have to do, because we swapped over the negative quadratic and made it positive, you just swap these brackets or the pieces in the bracket over. So we would have, and it doesn't matter when there's a plus, but I'll swap it over anyway, 3 plus 2x. And over here we have 4 minus 5x. Okay, so there are our brackets done, but obviously these pieces, the x's, should have been a cos, so we just want to replace that, which would mean that our numerator now wouldn't have the x there, but would have the cos, so our numerator would be 3 plus 2 cos theta, and next to that 4 minus 5 cos theta. There we go. And our denominator, if we write that in as well, was 3 plus 2 cos theta. Now if you have a look, obviously looking at this fraction here, you can see that we have a matching factor on the top and the bottom, which is the 3 plus 2 cos theta. So they can both be cancelled out, which means all we are left with is the 4 minus 5 cos theta. So all of that would go down to 4 minus 5 cos theta. And as you can see, that matches what we're being asked to find in the question, where we're being asked to show that it was always equal to 4 minus 5 cos theta. So we've managed to prove that for step 1. So this would be the first stage of this question. Obviously you can see that I've run out of a lot of space here, so I am going to have to get rid of this working, but we're going to have a look now at the second part of the question. So we'll get rid of all this working and we will have a look at the second part. Okay, so for the second part of this question, it says hence solve between 0 and 360, including 0 but not 360, the equation, and then it gives us the original equation, or the original pieces that we had there, but instead of putting theta, they've put x, but this time it doesn't say that it equals 4 minus 5 cos theta, it says that it is equal to 4 plus 3 sine x. Now we already know from the first part that all of that is going to be equal to 4 minus cos theta, and if we were to write that using the letter x, that would just be 4 minus 5 cos x. So we know that if both of them are equal to one another, that 4 minus 5 cos x is going to be equal to 4 plus 3 sine x. And that's going to be a little bit easier for us to use than that fraction. And again, you're seeing in this question, we're using the piece from the start to help us with the second part here. So the first thing we're going to want to do is set them equal to each other. So if we say that 4 plus, it doesn't matter which one we write first, let's just go for 4 plus 3 sine x, and that is going to be equal to 4 minus 5 cos x. Now again, we want to obviously solve this, so we want to get this to a point where it only has sin, cos or tan, and we'll think about how we could maybe get there. Now the first thing that you might notice here is there's a 4 on both sides, so we could minus 4 from both sides, and that would just leave us with 3 sine x, which is going to be equal to negative 5 cos x. So that would be our first step. That's gotten rid of a 4 from both sides. What we could now do to get it so it's just sine x or just cos x, and I'm just going to divide both sides by 3. That's going to remove the 3 from the start, and then we'll think about where we could go with next. So if we divide both sides by 3, that leaves us with sine x equals, which is going to be helpful, is equal to, and I'll just divide the negative 5 by the 3, so negative 5 thirds cos x. Now at this point here, you'd hopefully notice that one of our trig identities is going to get involved, and that is if we divide both sides by cos x, we're going to have sine x over cos x. Now we know from our trig identity that sine x divided by cos x is equal to tan x. So that is going to eliminate our two different trig pieces there, because now we're just going to have tan x. So if we do that, we would have sine x over tan x when we divide by cos x, sine x over cos x is going to equal negative 5 over 3. And again, you could write in what you've done there. We've just divided by cos x. There we go. And of course, sine x over cos x is equal to tan x. So we could just rewrite this that tan x is equal to minus 5 over 3. So that's going to be very important there, because now we're in a position where we can solve it. So at this point, we can do the inverse of tan and get our solution. So for tan minus 1, so we get our angle, and that's tan minus 1 of negative 5 over 3. If we type that into our calculator, we get the answer, and it comes out as minus 59.0. So we've got our first solution. Now, of course, that has fallen outside of our range that we were looking at, as we're only looking between 0 and 360. So for this, we are going to have to draw our tan graph, and we're going to have to visualize where those solutions are. So if we get rid of some of this working, and we can just draw the graph over here, and that's going to help us just to visualize that. So here we go. Let's just get rid of all of this. Lots of pieces there. But we want to draw this tan graph, and we want to draw a nice sketch of that. So if we draw some axes, again, our first wave goes through the origin, and then we have our asymptote at 90, and our next one goes up then through the 180, and our next asymptote is at 270. So that's going to go up through the centre there, and I've drawn that very badly, so we should probably draw that again. Again, it is just a sketch just to help you to visualise it, but it's good to draw it quite well. And our next one would start at 270, and it goes up through 360, so we could stop there, but of course that does actually carry on, but we don't need to draw the rest in because we're only going up to 360. So let's think about where that solution would lie. We've got negative 59.0, and that would go between 0 and the negative 90, where our other asymptote is. So it's going to be somewhere in the middle. Let's just imagine it falls just there if we were to trace that down. And then, of course, all we're going to do is go across. So we would go across, we'll hit the next curve just here, and then we're going to go across again, and we'll hit the next curve just there. Again, you might know some quick ways of jumping between these tan values, and again, if you use any of your quadrants and things like that, that's absolutely fine. But again, as I've explained before, I do like to visualize what these graphs look like, just to imagine where they're going to go. So for the first one, to jump between these two, it is just a jump of 180 degrees. So if this one here is negative 59, and let me just check it on the calculator, because it doesn't say in this question how to round it. It did come out as negative 59.04, so I'm going to give it to 2 decimal places just to make it a little bit more accurate. So negative 59.04, to jump to the next one there, all I need to do is add 180. So if we add 180 to that, it comes out as 120 and then 96 it comes out as. And there we go. So jumping on to the next one, I would go another 180, so plus 180 again, and that comes out as, on the calculator, that comes out as 300.96. And of course, if we jump to 180 again, it would go over our limit, which is 360 degrees. So these solutions here, we've got three solutions, negative 59.04, which is below zero, so we can't have that one, but we do have 120.96 and also 300.96. So we do have two solutions there. Again, we would round that as we see appropriate, so we could say that x is equal to 120.96. Of course, we could write that is equal to, or we could say 121 degrees to the nearest degree. And we also have x is equal to 300.96, or we could write that that is equal to 301 degrees, again just being to the nearest degree there. So obviously you can see this one is pretty tough. There was quite a lot of steps, but you can see a lot of similarity between these trigonometric equations, whereby we are isolating it down to either sin, cos or tan. We're doing the inverse to find the angle, and then we're just sketching it onto the graph so we can see how many solutions we've got. Okay, well done. That is the end of the video. I hope you enjoyed that. If you did, please don't forget to like, don't forget to comment, and don't forget to subscribe, and I'll see you for the next chapter.